of integration, and g of x will be it will be functions, algebraic functions on maybe in several variables. Yeah, and here there. Second, probably. Okay. This one is a typical example. Yeah, we integrate over some chain, maybe it's boundary. So there are, and here there are some cohomology theory. If you don't have exponential integrals, kind of simpler integrals, integral of some rational function, several variables over some cycle. There's a kind of big part of algebraic geometry that's responsible for calculation of these integrals called Hodge theory. In general, for usual integrals, if we have, let's say, algebraic variety, let's have a complex numbers, let's say smooth algebraic variety, then you can calculate, there's a kind of famous theorem by Grothendieck that you can calculate Gram cohomology of this variety algebraically. So if you consider the following thing, you consider X with the Zariski topology, if you do algebraic geometry, and consider of sheaf of algebraic differential forms with the Ram differential, and you calculate hypercohomology, it's pure algebra. Then it's isomorphic to usual, it's called H the Ram of X. It's isomorphic to usual topological cohomology. X is
X has to be smooth for that.
yeah, smooth. Yeah, okay. X with analytic topology, it's usual complex variety with complex coefficients, and it's called, and it contains actually integer lattice. H beta of X, which is just cohomology of X with integer coefficients, image is cohomology of integer coefficients. Yeah. And if variety is defined over rational numbers, it's in a vector space of rational numbers, such that it has the same dimension as these things. And now, if one put in the game exponents, there is a similar theory. It's not terribly well known, but in general, maybe I'll put small f. Now we have pair X is algebraic variety over C, algebraic variety, and we get a function from X to which we can consider map from F to a fine line, or the same as element of X. And this is a function, and one can put various factors like g of x, which I denoted before, in the front, and want to calculate these integrals. The story is the following. Now one can consider, it's not Grothendieck, but it's a generalization of it. Now consider X with the Zariski topology, and consider sheaf of forms, algebraic forms, but with differential will be d plus df, h by df. So secretly you multiply by forms by exponent of f, because it will be exponent of f times omega plus. Now, so consider hypercohomology of this thing, and the claim it's also has topological description. It's isomorphic to H beta of pair X and F, answering by complex numbers, where what is H beta of X and F is defined.
Definition of that symbol. What did you say?
Oh no, it will be some certain integer cohomology associated with variety in the function. No, I'm just going to define it.
Oh.
It's definition. What is this thing? Namely, you consider cohomology of pair. And you take image of some value t, where t, let's say it's a complex number, and real part is very negative, and it's stabilized, as a cohomology stabilized when real part of t goes to minus infinity. Now, in general, if consider fibers, will be some finitely many exceptional fibers when topology jumps, but otherwise it will be fibration, and so it is consider this kind of contractible domain, pick any point, define this. Yeah, so the comparison, how to identify one thing to another, it's very easy. How one can identify. First of all, we can assume that X is affine. It's if it's not affine, there is something called Johanna-Lu trick. If it's, let's say, quasi-projective variety, one can have a bundle with fibers affine spaces, which doesn't change topology, doesn't change any of this cohomology. So one can always replace by adding more variables to affine case. And affine case is hypercohomology considers as global sections. You consider forms, global forms with differential d plus df, or according to this thing, you consider closed forms of type such. Suppose we have a f omega will be global form of certain, so let's say, certain degree k, some algebraic form on X, and such that it's closed. How we can integrate it? We consider dual space will be homology of pairs. And homology of pair one can realize in the following way. So we get X, which maps to just plane C. And we pick some compact domain which will be in C. We consider in C. Consider the following thing. We consider negative part of the real axis union with some disk. Zero with some sufficiently large radius, and we consider chains which sits in the pullback of this thing, and any element on dual space we can represent by such a chain, and over such chain, if it behaves well at minus infinity, we can integrate exponent of f times omega because it will be exponentially convergent integral. Yeah, so that's an identification between this cohomology. You consider pullback of such figure, yeah, and consider chains which are proper over this figure. Some kind of chain, non-compact chain, such which is properly maps to C, and image belongs to this figure. And appropriate and. Yeah, and because it's topologically fibration, we can assume that on this part of the array, it's kind of locally constant family of chains and fibers. Then the integrals convergent. Okay, yeah. So that's this identification, and now, so it's in my sorry, best. Okay, okay. Best, no best. Why? Oh, okay.
Let's take your vest off. If you put it.
Just on the vest.
Yeah, because it's rubbing up against your shirt.
Oops, one second.
So, yeah.
Like here? Okay. Now, so that you have kind of abstract algebraic story equivalent to isomorphic to topological story, and the same thing with two lattices can be set in.
What's the relationship between the integrals you're talking about and the cohomology?
Sorry?
What's the relationship between these integrals?
Yeah, if we have closed cycle, but it's non-compact, not like here, it's a bit more complicated. It has boundary inside. Then this integral, it's what? If you consider top degree form, will be closed automatically. It will represent some cohomology class, and we integrate over chain. It's pairing between some integer vector in dual space.
Something is exact if it's integrals over certain sets of cycles.
Yes. It's absolutely the same story as for usual algebraic geometry, but with exponential function. Yeah. So that's. I think my first talk will be, I will discuss purely finite dimensional algebraic situation, and the second talk I will say what one can say about infinite dimension, because it looks at using some machinery, one can define rigorously these things in infinite dimension without saying what is Feynman integral. Yeah, so f will be action functional, and it will be second part of the talk. So now I'll just describe what is. There's a really interesting structure on these two sides, and I'll describe it under some assumption, which is really important. Assumption f is a proper map as a map to complex line. So it already excludes the case of affine varieties, because then the fibers will be affine. But in many situations, one can easily compactify fibers and achieve the situation that fibers will be proper maps. Then the following happens. So we introduce a small parameter h bar, Planck constant. And now we can just rescale our cohomology. Yeah, this I called maybe h the run of x and f. Then we have a family of cohomology depending on parameter h bar.
Can you give an example of a proper map?
Yeah. Yeah, there's some typical things coming from mirror symmetry. We will consider x contains some kind of open part, which is c star squared. Coordinates z1, z2. And we consider maps to c given by z1, z2 goes to z1 plus z2 plus 1 over z1 plus times z2. It's a typical example. And then we consider what is the fiber of the thing. The fiber is elliptic curve minus 3 points. For some values, critical values, this elliptic curve is degenerate, but still it's elliptic curve, maybe not elliptic curve minus 3 smooth points. And you just add the 3 smooth points, so it's not convenient to write as equations, solution of equations, but add these points. No, that's the simplest natural example. Okay. Yeah, so what happens then? We have this drum cohomology, and then we know it's isomorphic to this beta cohomology. X the same f divided by h, maybe complex numbers. And this cohomology is a cohomology of pair, yeah? And because it's cohomology of pair, they form a local system over C star, this kind of coordinate h bar. Because under this condition, you rotate a little bit, you can identify cohomology, but globally there will be some non-trivial monodromy. Okay, so get this family of lattices, but claim that if you forget about right-hand side, this left-hand side has natural limit when h bar goes to 0. Limit to extension as h bar goes to 0. And what is this? How to describe this limit? When I substitute cohomology with the things, you can just rescale the same as hypercohomology of x Zariski omega algebraic and hd plus df. And now I can go to limit h bar goes to 0. And this limit is hypercohomology of x with Zariski topology of forms with differential just wedge product with df. So this is a non-trivial theorem. So the theorem, the dimension of this cohomology space doesn't jump when h bar goes to 0. So theorem that this cohomology is a vector bundle over C. Not C star with coordinate C0, or equivalently that the total dimension of hypercohomology of h dram xf divided by h bar is equal to dimension of hypercohomology of x forms with df. Yeah. Here there's no h bar.
No, the vector bundle over C sub h bar.
Coordinates with coordinate h bar. The coordinate on the C is h bar. In fact, this cohomology in this assumption one can calculate again in analytic topology, because when the map is proper, this complex of shifts is non-trivial only on compact part when which is critical locus. Okay, so we have a family of cohomology with lattice when h bar equal to 0 and some limit when h bar is equal to 0. And the final structure is that the fiber when h bar equal to 0 maybe I'll denote it. Oops. Okay, let me denote it. This limiting fiber divided to 0 is this guy naturally splits in a direct sum over following thing. So we have my variety which maps to C, and now we have a critical locus. And critical locus function is the union of some connected components. And connected components could be points, could be isolated critical points, but could be not isolated critical points. Could be very singular subvarieties. this multiplication by df is give an exact complex outside of singularities, so it's a direct sum of contribution of some small neighborhoods of of the alpha. For this one can say the following: you can consider hypercohomology of kind of neighborhood of the alpha with omega with differential by df.
What?
Of neighborhood.
Link.
Some neighborhood, open neighborhood. Any open neighborhood, small neighborhood, which doesn't touch as a component. So you get this direct sum decomposition. Now this theorem is the story of the theorem is a bit complicated. It's something like maybe 20 years ago. We proved it with Sergei Barannikov, and the proof was similar to proof of Gortin-Dick theorem. We use of course there was some kind of compactification, resolution of singularities, log forms. But here it's a bit more complicated than log forms. One needs introduce some Sobolev spaces and some analysis, DD bar lemma. Okay, but then we never wrote it up, and then people resurrected different proofs, but like Lord Sabah, and it became standard. So this cohomology do not jump when the map is proper. Phone? Oh, maybe, but it's different. Where's my phone? Maybe I'll put it. Okay. So that's it's the isomorphism, and one can make something even more from this. There is another.
So the dimensions of the fibers jump around.
Sorry?
The dimensions of the critical loci jump around.
Would be different. Critical loci can have very different dimensions. Could be very singular. The only thing which you can say is that function on each connect component is constant because it's critical locus. So each maps to some critical points, but maybe several critical loci maps to the same point. Now I can say something a little bit more. For each critical component,
Fibers are all the same, right?
dimension of the fibers, in principle they all the same, but in principle one can assume that function is equal to 0 on your variety. But empty varieties also has the same dimensions. Maybe you're right, No, dimension of fibers are the same, but critical loci it could be very general. Maybe before going on, I just want to make some remark about this cohomology. For each component, the alpha of critical locus one can make a kind of local picture. One define kind of local Betti and de Rham cohomology. Because this was only for h bar non-equal to 0, but equal to 0, but now for h bar non-equal to 0. The definition is the following. How define this de Rham cohomology so the de Rham in Betti. The de Rham cohomology one can define the following way. One consider hypercohomology of, let's say, formal neighborhood, or if you use algebraic geometry, or open neighborhood in algebraic geometry of the alpha, with coefficients as forms. Now you add Planck constant, and you consider this cohomology. This cohomology form, again, a vector bundle of a formal disk. And this bundle will have a natural formal connection with second order pole on H bar, because you kind of, when H bar is inverted, put Laurent polynomials, you kind of replace by differential d plus df, and you use kind of Gauss-Manning connection along H bar. So it has some flat connection with second order pole. But I claim that this connection has essentially regular singularity.
You mean on the deleted formal neighborhood?
On deleted formal neighborhood, yeah, you get a connection, yeah. And it has second order pole if you write in the trivialization. And this connection will be the following. It will be d plus 1 over h bar square times f alpha times identity matrix plus 1 over h square something nilpotent plus some other part. What I say is that if consider this connection minus maybe dh bar minus f alpha dh bar over h bar square has a regular singularity. Yeah, after removing small constant, you get a regular singularity, and then it means you can extend it. It's meromorphically equivalent to collection with first order pole, and then you can extend it. I have to remove something. The vector bundle has a connection some canonical connection coming from since Gauss-Manning connection, and then delta minus f alpha divided by h bar square has regular singularity, and that implies that this bundle with connection one can extend to bundle over C. In canonical way with connection. Yeah, so this means that this hypercohomology, although it looks something called formal power series, start to make sense when h bar is any non-zero complex numbers as well. Yeah, it's pretty delicate construction, and again this the theorem which was proven about a couple of years ago by Motohiko Saito. And Claude Sabat said that this thing is bundle over C star with flat connection is naturally isomorphic to things coming from vanishing cycles. Local system coming from vanishing cycles, namely, what is this? You consider hypercohomology of this Z alpha, and then you should put something called sheaf of vanishing cycles, and you consider f minus f alpha maybe divided by.
So now you're looking near one critical value.
Yeah. What I'm doing here, this will be better realization. Namely, I have my critical component of my critical locus. It's compact, and I take a small neighborhood, maybe tubular neighborhood with small radius. And what I do, I define something like Milnor fiber. Called Milnor fiber. Instead of thinking what is the vanishing sheaf of vanishing cycles, so on, one can give definition at once. Namely, I consider a cohomology of pair, this tubular neighborhood, and take preimage of what? I take value f alpha, and now remove a very small h bar, maybe multiplied by a very small number epsilon.
I apologize very much. And there we go. Sorry about that.
Let's assume that h bar is any given number, like positive number. Just move a little bit of my critical value to negative dimension. I don't move not much, but very little bit, and consider this fiber and a cohomology of the pair. And this form again local system, because when I rotate this point around, I get locally isomorphic but globally not isomorphic homology. Yeah, so there's a kind of similar picture locally. For each critical locus, one get some homology depending on small parameter which has a limit, and when parameter is non-zero, you get a lattice. You get good notion of cycles. In C, yeah. No, this no, this disk, this neighborhood is in ambient space. Your alpha is in. Now epsilon is small, so consider neighborhood of my critical locus, and it maps to some neighborhood of f alpha. And I consider fiber very close to f alpha, but we can say negative direction, and consider homology of pair. Yeah, so this reminds this, for isolated critical points, it's exactly definition of Milnor fiber. Yeah, so it's generalization of Milnor fiber to non-isolated singularity, and maybe I'll just say it. For isolated singularities, this de Rham cohomology. Sorry, maybe I should say this. How do you denote them? I have this kind of a local de Rham cohomology of local near the alpha x f, and maybe divided by each bar equal to 0. It's exactly so there's de Rham realization and Betti realization. The Rham realization is a Jacobian ring for singularity. Consider if we have maybe some. My z alpha is just 1 point, x0. I consider O of x0 and divide by ideal generated by a derivative of functions. With the I local coordinates. It's Jacobian and Betti cohomology is cohomology of pair. I consider cohomology of Milnor fiber, which means that I consider a small ball near my point and consider f minus 1 of closed value. And it's and the pair is homotopy equivalent to a bunch of bouquet of spheres, and so the cohomology will be in the middle degree. So all the things are in the middle degree. It's actually not but maybe top degree forms. And omega n. Strictly speaking, this is cohomology top degree forms, and here's middle cohomology pair. N is dimension. Now you see that in the case of isolated singularity, we get this classical story about how we call it Milnor number, analytically or topologically. And what I explained that it's for non-isolated singularities, you under this very mild assumption that the thing is compact, you also have this generalization. Now there's a really important remark. It's some kind of the stability of Milnor numbers. Suppose you get a function which depends on some parameter. S, Fs. Where S belonging to some parameter space. You get a family of functions. And suppose that f of 0 has isolated critical point. And it has some Milnor number.
That's this middle Betti number?
Yeah, middle Betti number, yeah. If it's a little number, it will be some positive integer number. But now, if you move a little bit your function, this isolated singularity will decompose in several critical points. You get some new numbers, mu I, whatever. Find many numbers. And then mu is equal to sum of mu I. The reason is, in a sense, obvious. If you deform a bit singularity, you just do not change topology of this ball, of the whole neighborhood and fibers. Yeah. And the claim is the same. This Milnor number, the same happens for this when singularities are not isolated. If namely, what I say, if singularity is not isolated, one can calculate kind of Poincare polynomial of cohomology of pair. So. The stability for Poincare polynomials. Namely, for each singularity, for each kind of component of singular locus, one can assert some polynomial, namely sum over maybe integers, let's say, I from minus dimension and to plus n is the dimension of my manifold, and consider, let's say, variable whatever t to power I, and rank of n plus h cohomology of this pair. U alpha and f minus 1 of alpha minus alpha epsilon. Now, so I get a polynomial with non-integer coefficients, and this polynomial it's so if consider this I and rank of hi n plus ai is invariant when I goes to minus I. It's Laurent polynomial because I shift variable by centered in the middle dimension, and it also have a if my variety is quasi-projective, it also has a bell-like shape, so it's first increasing and then decreasing because of one can introduce like in usual break situation primitive classes and the same story.
Is this some kind of Poincare duality?
Yeah, this is Poincare duality. Yeah, when you replace h bar by minus h bar, then one can have a perfect pairing on this. Yeah. Now, so the case of isolated singularity, it means that all this Poincare polynomial is a constant. I have only because of my shift of grading. And the claim, it's I think it's kind of new. It's new observation. I never saw it. It's very trivial observation. Then, if you deform function with non-isolated critical points but still compact set, then this compact set will decompose in several components. Then these polynomials will be equal to the sum of polynomials. And topologically, it's essentially almost trivial. The same thing happens like for Milnor number. And in particular, it says that consider the degree of this polynomial will be the dimension of this degree of this polynomial is equal to the dimension of the alpha of. So it means that this what we kind of assumed from C infinity situation that generically deform singularity and it will be became only more singularities. It's completely wrong in complex world. It's true for isolated singularities, but if they form high-dimensional loci and they are compacted, that's the main point. Then the things cannot disappear. And in a sense, it's.
In the ISA case, the dimension is 0 or something?
Yeah, dimension is 0 and degrees polynomial is 0, just constant functions, Milnor number. Yeah, and why it's important? Because in physics, people consider critical points of superpotential, things like this, and when you have supersymmetry. And we get some varieties and consider essentially this cohomology of these vanishing cycles. But when they consider it, they do it on classical situations. It's not clear what quantum correction can do. No, in principle.
Usually there is some formula.
When we can write it like Poisson summation, when we can reduce it to the isolated critical points. So from one side, the manifolds which are critical, and from the other side, it's isolated critical. We call.
Yeah, no, it's a different story.
use it all.
No. But in general, I just want to say that if you even don't do any supersymmetry, if you have this maybe in some infinite dimensional space, yeah, this argument is actually very stable. First of all, I claim that these things one can define when my variety is infinite dimensional. Yeah, imagine that X is some infinite dimensional space, like space of fields, but with values in some complex target. So this is some infinite dimensional complex manifold, and we get some function. What we want to have this critical loss to be finite dimensional, and for this, what is guaranteed, what is necessary. This maybe if you wasn't. Yeah, so I should stop maybe.
I think you started about 20 after.
Sorry? Yes. Okay. Yeah. Yeah. Infinite dimensional case. X is some kind of infinite dimensional complex manifold. And assume that second derivative of f is Fredholm. F is some holomorphic function, and second derivative is Fredholm. And then it means that critical loci are a solution of some nonlinear equation with Fredholm symbol, and so it means that they're finite dimensional.
At the critical point.
Sorry?
At the critical point.
Oh, a family of critical points. Yeah, they automatically form
This condition is
at critical points, yeah. It implies that Z alpha are finite dimensional spaces, and then it essentially says that you can kill almost all coordinates, local coordinates near Z alpha. One can kill because in this direction the function will be purely quadratic. It's like if you have function infinitely many or very large number of variables, this is stabilization at quadratic, non-degenerate quadratic form extra variables. Yeah, so it means that one can reduce to finite dimensional situation, and you are done. The cohomology depends on the reduction. Everything is well defined. But there is a little caveat here, which is very important. Caveat. When you reduce to finite dimensional situation, finite dimensional times some kind of infinite dimensional with quadratic form. And here, yeah. So essentially, what happens? You can assume that you get kind of Z alpha finite. You get some finite dimensional situation with some function also. Whatever. Still, they have tilde. It's finite dimensional. And or times some infinite dimensional space with quadratic form. But in fact, it's not times, it's actually bundle. It's a bundle with quadratic form. And then we make its different identification. You essentially replace a finite dimensional situation. You add finite dimensional bundle with vector with quadratic form. And this quadratic form this could be a problem with this quadratic form. Because the quadratic form gives you two different quadratic forms differ, the determinants differ by Z mod 2 torsor. And when you calculate cohomology, you have some ambiguity. You either calculate cohomology or cohomology with coefficients with some plus minus 1 monodromy local system. And that should be fixed somehow, and this data. And this appears in some story called Donaldson-Thomas invariant. This is called orientation data. It's really a real life problem to fix this plus minus 1 sign in compatible way, and this is some extra things some extra care what should take when we go to finite dimension, but I will ignore this thing in the rest of my talk. So ambiguity is it's H1 of the alpha with z mod 2, tensoring by some local system. So in fact, there are maybe several cohomology depending on various z mod 2 problems. Okay. So that's now kind of the last things which I want to describe you. This relation between many. If what is the rank of z mod 2 cohomology description z mod 2? Yeah, get kind of should maybe have all of them. I don't know. In general, I don't know what is a good way out from this problem. Now, just one or two things I have to say about relation between local and global. So we have two pictures. When we have global picture, we get cohomology depending on h bar, h beta, which form kind of local system of lattices over C star. And then if we tensor by C, this vector space has a limit as h bar goes equal to 0, which I explained. Yeah, that's the main point. And locally we also have similar things. We have for each connected component we get same story. So now we get sum of all connected components of critical locus. Of the same things. So for h beta, local near the alpha, and also we get a limit when h bar equals to 0. Limits. Here's limits is really direct sum, which I explained. But before limits, it's not direct. It's a different story. Actually, they're not equal, but limits are, when h bar equals not to 0. They are not isomorphic, but when h bar equals to 0, they are isomorphic. Now, so the question how one can make them isomorphic, namely, let's choose a generic ray in h bar plane. Ray.
Yeah.
Bar plane. And what does it mean, generic? So it means that if consider critical values of f, or you get a finite set, and you rotate it in such a way that all things, all critical values have a different imaginary part. Yeah, so, and in this case, yeah, so if I rotate, all critical values will have different imaginary part. And then what I can do, I can consider cycles for integration for my exponential integrals, which project exactly to this r minus plus critical value. So I can consider chains of integrations, and this chains of integration will be identified with local things which I have. Then I have canonical isomorphism between chains of integration of global integrals and direct sum of local integrals. And when I rotate, so I start to rotate these things, there will be Stokes directions, kind of non-generic Stokes direction when I have two rays coincide. Then when I cross the Stokes direction in H plane, this identification will jump. Yeah. So that's essentially yeah. So this isomorphism jumps for x belonging to some finite set of Stokes rays, which are kind of non-generic. Maybe I'll stop here for a moment. Yeah, I'll continue how this jumps, but the claim that these things kind of start to make sense in infinite dimensional things as well. You can, and actually Witten discusses it a lot, but in his papers about complexification of Chern-Simons. So we'll continue the story after the afternoon.
So is the statement, if you pick a generic ray, then you get an isomorphism?
Yeah.
Constant locally, but as you cross these directions?
Yeah. So in a sense, yeah. So the story is the following: one can really start with this local data and certain additional data, how isomorphism change when you go through Stokes rays. It will be some kind of roughly number of instant, kind of some instantons somewhere. So it will be some pure topological data relating different local data, and then from this you can canonically reconstruct global structure.
Are these rings, or are they just?
No, they're not rings. It's just
They're pairing though.
this is pairing when h bar goes to minus h bar.
What?
This is pairing when h bar goes to minus h bar in two opposite ways. Yeah. And it's rings. I wouldn't consider them as rings. Yeah. It's kind of small. Okay, thank you.
Questions? If not, let's say I'll see you again. Go by in this room.